you have any questions on anything? Any questions on anything? No? We'll give inLab06 and Lab6 a higher priority. We'll go through the code and repeat the things we have to repeat. I know it's impossible for you to learn everything by just learning that or listening to that for once, right? So the best way to learn is to repeat. Let's start with the calculation first. Then we get into the overall diagram of the hardware, then the software, okay? So if I draw this is your old friend. Doesn't have a last name, right? Just PWM. Your old friend. If the frequency here is given 38 kilohertz, what is the period? 1 over 38K, right? What is it? I'll just give it to you to save time. 26.3 microseconds. Right? This is being controlled by what? Which timer? Seriously? Did you all fail the midterm exam? Haven't graded yet. Controlled by which timer? Timer 2. Which? Oh, because I didn't ask that question on the exam, that's why I didn't know that.
Oh, I didn't figure out the name question.
All right, we'll see. Oh, I will have to grade it.
I'll give you timer 4 too.
Timer 4? Could be.
Or timer 6.
I think so, yeah.
Timer 8.
So it's just in the drop-down menu, just pick up timer 4 instead of timer 2, right? Should work. Which register controls that? PR2 for our case, right?
Wait, the first one, history.
All right. Why is PR2 not like PR3 or PR4? Because it's PWM2, I think,
That would be 8 bits.
or PR2. PR2 is the independent timer, right?
Yeah. It's a register.
Oh, actually PR2, you are right. So PR2 is part of timer because that's how timer 2, get timer 2's flag got set, right? Because it's comparing to PR2. Good. All right, let's do a calculation. And keep in mind that the timer 2 prescaler we use in the lab is 124. Okay. Keep that in mind. The second thing I want to talk about is hardware really quick. Ground, VCC. That's a decoder. That's an IR decoder. To make you familiar with the hardware. So what is this pin?
VL.
Yes, VL, and also connect to where?
RC0.
RC0. Okay. Let's keep going. I write it down here so I'll come back to this page later. It's important to write this down now so you know what's happening. And there's so for items 3, there's a little header with 2 pins on it and connected with a resistor and then the BJT transistor with the IR LED on the top. There's a little resistor at the bottom. It's going to ask you to calculate the voltage and currents in Lab 7, not Lab 6. But in Lab 6, you still need to know that this is a switch. Okay. So you have to make a jumper, put a little jumper on the top to make a connection. And so what's the pin here? Input or output? This pin. Wait, to pick. If we're talking about the pick microcontroller, is this pin output or input? See? That's why I have to repeat it. To pick. This is the decoder, right? So this is the input or output? Input. Why?
Because it's reading from decoder to the pick.
Yeah, decoder receives the signal and output to the pick, right? So that's a pick input. What about this though?
Which device
This is the emitter.
Oh,
IRLED.
Out from the,
What's the name of the pin? Remember?
no, I don't remember.
Okay. It's okay. I will just write it down. RC1. Okay, RC1. So why RC1? Let's take a look.
Connect to CCP1.
CCP1, yes. Let's go to the website. RC1, oh, CCP2. That's all right. Yeah. RC1 is CCP2. So what's the difference of CCP1 and CCP2?
CCP2 goes with timer 2.
No. Let's come back here. Let's just do it back and forth and repeat it. So eventually you will remember that. Remember, I even made a mistake as well. Remember everything. So RC1 is basically what? I just showed you on the pinout.
CCP2.
CCP2. So CCP1 or CCP2, they are what? They are pins, right? So what about CCPR? H. That's a register. Register. So you got another one, it's called CCPRL, remember? It'll concatenate that with what? To form that 10-bit thing that you hate so much?
D.
DCXB, right? How many bits? 10. Whenever PR2, timer 2 reaches PR2's value, it's going to send CCPRL to CCPRH. But keep duplicating this here as well to form that 10-bit count for your timer 2 to match. So timer 2 is here to match with this guy. So here's the LSB, that's 10-bit overall, right? So what's the frequency of this LSB is being toggled at?
64 megahertz.
Or FOSC, right? Okay, where's PR2? Here. If I repeat this for 100 times, I don't believe you could remember it.
Prescaler then too, since timer 2 has.
Oh yeah, 4, right?
Yeah.
Yeah. Okay, good. It's been like 5 or 6 times already. So it's comparing with PR2. PR2 is shifted. So what's the frequency of this bit being toggled at?
FOSC before the prescaler.
Make sense? If you don't understand it, you should seal this in your mind. It's been so many times. Okay, so we are thinking, hey, RC1 is connected to CCP2, and CCP2 is for what? PWM what? CCP2 is for what? PWM2 module. Okay? CCP1 is for PW2 modules, PWM module 1. And CCP2 is the output of PWM module 2. Okay? So, because we are outputting PWM to where? Again, we didn't answer this question. So this is the input or output. It's so simple, right? So
For the PIC?
for the PIC, it's the input or output. Output, right? It's the output for the PIC because outputting PWM waveforms.
Yeah.
Make sense? Back there? Okay? So you are outputting a PWM. Make a jumper, the PWM electrical waveform will reach here. Okay? We'll toggle this, it's the base terminal, it's a B, C, E. It's a collector. This is the base terminal, that's the emitter. Terminal of the BJT transistor. So it's the B, C, E, just the names of the terminals. So if you toggle this base terminal, it's just a resistor to limit the current because this is just a single dial over here. Internally, it's a NPN, so the PN junction is a diode. That's why you need a current limit resistor, otherwise it's gonna burn this little thing. So you toggle base will turn this on and off as well. So the channel here will have a current on and off following this pattern. What's happening? What's going to happen?
When it's low, it's going to be on.
Yes. No.
Yeah.
High will be on
Why?
because it turns on. The channel is on, so this will be on. What's
So
that?
won't there be zero voltage drop if it's on over the diode?
No, because it's not ground. If you turn this off, there's no current flow because this is disconnected.
If it's zero, it's off.
If zero is no, if yes, if it's zero, it's disconnected. If it's zero, it's a switch, right? You cut it, disconnect it. If it's zero, disconnected, so there's no current because it's not grounded. It's like something floating in the air. It's not grounded, not forming a loop. If it's on, this turned on, you connect this point to ground, so you got current flow.
Oh.
You got current flow emits IR light. So that's why this IR pulse is going to follow this pattern, right? And this is light. Keep in mind, this is light. You are not able to probe it. You can probe the electrical signal probably here. It's going to be inversed or here. I don't know. But anyway, so it's going to emit light pulse like this. Okay?
Could you break down how the BJT works a little more?
Whenever this turns on, it flows a little current into here, into the base. And that current is performing as a turn on current, and will, because the BJT has a certain current gain, it's usually beta, could be 90 or 100, and the so the collector terminal will form a current to be IB times beta, so it's flowing current through here. It's a current control current source. Anyway, so when you turn this on, the PN junction here is on, and it's gonna form a collector current going from the top to bottom, from collector to emitter.
Okay.
And because this is a remember KCL? It's basically these two currents adding together to form IE. So IE is slightly bigger than IC because you have a little current here as an input. The reason why this is a current control current source is because if you just look at this equation. IC is I times beta, so it's current controlled and give you a current output. There's no voltage control. So voltage control current source is a CMOS transistor. There's a gate, it's a dielectric material, so there's no direct contact. It's using electric field to turn on and off the channel. So it's got current flowing from top to bottom, but there's no direct current injected into the CMOS transistor. For BJT is different. That's why BJTs are not being used for high level or very large scale integrated circuits. The reason for that is it's consuming a lot of power, and also you cannot make this too small, as small as the CMOS transistors. So these are huge and consume a lot of power. Whenever it's off, it's still leaking current into it. And whenever it's on, it's also using a current going through it to get another bigger current from the collector. So it's always running current into the transistor. For here, you don't have actually a direct current going through the channel. It's just using electric field. You turn on that voltage, it creates an electric field. It's going to turn on the channel. So there's no direct contact. It's gonna so it's way lower power consumption compared to BJTs. Back like maybe 60 to 70 years ago, people start using BJTs in the circuits. They couldn't scale it down. First, they cannot manufacture BJTs too small. Second, it's consuming too much power. If you put too many of them on a single circuit, you cannot use the LiPo battery to power up your devices. So you have to use these ones. So all the devices are using CMOS now. All the devices you have, smartphones, all these ones are CMOS transistors. But they are still being used for power devices, for like power switch. So for here, you don't really care about the power consumption, just the switch. Okay, so this one is being emitted by the IR LED, and this will be received by by the decoder, right? By the decoder. The decoder is, I'll just draw it here. The decoder in the middle. Remember, here's a VL. I'm just repeating. What's a VL pin? What's the VL pin here? Remember the decoder? RC0. Okay? What's the PWM pin? RC1. Okay. So RC0 is nothing special. It's just the GPIO. General purpose IO, right? GPIO. So if we use 26.3 microseconds for the period, again, why do we choose this as a period of the PWM waveform? Why?
Because it's 38 kilohertz.
Because 38 kilohertz. That's usually the decoder is designed to just receive or respond to 38 kilohertz. Okay? Or it's repeating. Okay? 38 kilohertz. That's why we have to use this one. So for timer 2, before we decide which prescaler that to use, we remember we drew a table. There are 3 options, right? So timer 2, and I have time to overflow, and I have period. Why is there different? This doesn't work as well. That's it. So how many counts do you have in timer 2 whenever it overflows?
256.
255 actually, it's the 8-bit. It's confusing people. Why is 8-bit again? It's 10-bit. You just told us it's 10-bit.
You have to add one though.
You add 2 bits. You add concatenate the 8 bits with 2 bits just for the duty value count match, but not for PR2 PR2 match. For PR2, you only use 8 bits, the upper 8 bits, right? Okay. Timer 2, 255, 255, 255. That's the maximum counts you have for timer 2, right? So the time to overflow is what? Time to overflow for this prescaler. Again, so this here is being toggled as this, right? Okay? So it's gonna be what? What's the frequency? 16 megahertz, right? 16 megahertz, because the 1-to-1 prescaler. We don't have this. It's 16 megahertz. 1-to-1 prescaler, 16 megahertz. So how long it takes? That's how long it takes to overflow. What's that?
Don't we add one?
Yeah, add 1 here. Wait for a second. So what about the second prescaler? 255 divided by 16 mega.
Over 4
255. Oh, over 4. As this is over 16, right? What about the period? Remember the period is comparing to PR2, not overflowing itself, right? So it has to add 1 to it because of the equation provided by the datasheet. For details, I don't even know because they didn't provide us with the digital circuits. We just need to know that the period for this prescaler is giving us 255 plus 1 over 16 mega, right? This is 255 plus 1 over 4 mega, and this is 255 plus 1 over 1 mega. Let me add another column here. In microsecond. What are they? 16 microseconds for the first one, and 64 microseconds for the second one, and 256 microseconds for the last one, right? Okay? Because the PWM requires a 26.3 microsecond period, and you don't answer, but why? I'm just repeating this, right? So we know that the prescaler can provide us with all the different 3 options, right? Okay? So we want to pick up which one to use. And now we need this. We need this. Okay? Why do we need this? On the back. Why do we need this? See? Because this. That's a requirement of the decoder. The decoder requires us to provide a period of 30 of this. Okay? All right? Good? Over there? Good? Okay. So since this is required, and these are all the options, So we want to pick up which prescaler for this application. This, because this is too short, this is too much, this works. So we can give an initial value to timer 2 to reach this period. Because the overall period, the maximum this can provide is going to be 64 microseconds. And I just give a little starting value in timer 2 so I can easily reach this period. Okay? So that's why we pick up this prescaler. Let me go to the next one. So what's happening is for the module ECCP2 module, remember in the ECCP2 in the resource in the microcontroller, this is what? PWM2 module. And it uses CCP2 pin to control as the output. So CCP2 on the pin out is what? Is RC what? RC1. RC1 connect to where? The BJT. Okay, cool. For the UART, EUSART, people are asking what's the difference between ESUART and UART. So the microchip engineers, digital engineers, they added some features to the UART pin, but UART is just UART. You put it down, the protocol is the same. You put it down to 0 as a start bit, and you output the data, and then you put it up. That's the same protocol. It's not changing. It's just UART. Okay? So EUSART1. All right, let's go back to the pin out. Let's find it. Where is it? Tell me. Here. RX1, TX1, that's UR1. And what are the pins correspondingly? Yeah? Oh, I mean here. So RX is RC7, right? And TX is RC6. Do we really care about it? Do you really need to do something to it for these? Or by far, have you done anything to it? Why?
Because it's already set up.
Already set up. It's hardware. It's connected on the PCB. So that is a UR port connected to your laptop. If you plug in the USB, right? You see the signals from PuTTY, or you can send signal or receive signals through here. Let me draw on another paper. I'll keep this paper here. Laptop, your USB, PIC. So PIC's RX1, TX1 is connected to your laptops, even though it's already being converted, but there's a UART to a USB converter. Let's just treat this one as a usual, just common microcontroller device. So RX should be connected to TX, and TX should be connected to RX. That makes sense, right? So this is receiving, this is transmitting, so this is receiving. And this is transmitting, so this is receiving. That's usually how you do the connections with UART protocols. So apparently, looking at this, RX1 is RC7 and TX1 is RC6, right? We don't really care about it because it's already hardware connected on the PIC. It's directly sending and receiving through the two wires. You couldn't even see it's in the USB mini or micro. Which one? So the micro is connected to where? To the snap. That's used to download the code to your PIC. However, it's not UART. Keep that in mind. If you are trying to debug, you see, hey, I'm not seeing that COM port. I'm not seeing the COM port on my computer. Which one is having a problem, possibly? It's only possibly something to the mini cable if there's something wrong to the cable. If you replace the micro cable, it's not changing anything, because the UART connections are connecting through the mini cable, the bigger one. Okay. What's the rate? What's the bit rate?
You get to choose the rate.
You can change it through PuTTY, right? Okay. You can change it through. So if you want to change it here in UART1, you have to change it through PuTTY as well accordingly, so they match. Okay. I have my signal here. You put a jumper here. BJT, IR, LED. What is this one again? RC1. Connect to where again? CCP2 is what? PWM module 2. Okay? Sending PWM light signal out. And you got a decoder. What is this? RC0. So receive the signal, output the signal to where? RC0. RC0 is what? GPIO. Can you receive a digital signal with a certain protocol through a GPIO? Yes, but you have to hand code it, the protocol with a certain time delays, because this doesn't have a digital block to automatically receive this data. Because, for example, you have a data like this. Here, the light signal here, like this, right? That's PWM. And assuming this is 1 bit, so the decoder is going to output the electrical signal looks like what? 0, 1, 0, 0. 2 bits. All right? So it's just a digital signal. So RC0 is looking at this signal. If you don't program it accordingly, does it know what is going on here? Just reading 0 and 1s. What is going on?
What makes it low when you're getting that PWM?
Yes, there's a circuit inside. It's easy to do though, but I just don't know. I haven't looked into that yet. It's easy. Inverters, right? Whatever. You can do it with like millions of different ways. So this one comes in. You have to know the certain protocol time delays. You have to know that this is 1 bit and this is 2 bits. So right here, right here, right here, right here, we got 4 bits instead of 1, 2, 3 bits. So RC0 cannot do the job. Okay. Now let's introduce EUSART what? 2. Why? UART1 is getting occupied by PuTTY, by the cable. Which cable? USB? Micro mini. Mini. Okay? Is that all connected now? All right, let's see. What are the pins for EUSART2? So definitely you have RX2, TX2, and what are the pins? Let's go back.
RB7, RB6.
What are they? I marked it for you.
Oh, he has them. B7 and B6.
Okay. So you have a UART module. So if you have programmed any Verilog, you know that it's a digital circuits, right? So the UART module is digital circuits, has all the buffers and everything. So that's a module, it's a block taking a certain area. So you have RB6, RB7, which is serving as TX2 and RX2. Okay, so which one you want to use here? For which purpose? Where are you at right now?
Do we want to receive the signal?
On the receiving the signal comes into RC0. and it's a GPIO. It doesn't have a certain digital block. I have to write a soft. It's called, have you done that before? It's called soft UART or soft serial. Have you done that before? Yeah, you can write a code to form that to deal with the timing. So it's something like you read it, you delay it, and then you read it again, right? So you can code it into your software to make this a UART. So you can do UART with Verilog, and you synthesize and fabricate it in the chip as a digital block. If you don't have that one, GPLs, you can also write RX and TX. So you know the timing. So simple, right? Just like put it down. You know the first bit is just a 0 starting bit. You just discard it. You read 0. You know the next one will be the data. Then keep reading for a byte. Okay, and then you detect a 1. You know it's done. So you can write a C code to deal with that. Easy. So, but we don't want to do that. Okay, so we can use this hardware to figure that out. So we need to connect the jumper wire to where?
B7.
Yeah. Why? It's RX, it's receiving, right? Okay? Then what? You're thinking, hey, can I use this to use TX because it's already received something, so I can use TX to send it out. Do you need it? Do you need that? Why?
It's on the board.
Do you have a so TX is used to send to a RX to another UART, to the external UART. If you have another UART device, for example, there's a OLED display, right? So the OLED display has a UART module here, has the RX and TX. Then you can do this, TX to RX.
We don't need to send something out though, right?
We don't.
Okay.
Since we don't even have a display module. So, but you want to see what's going on, right? You receive the data, you want to see if it's right. That's the whole goal here. That's the overall goal here. You're sending an IR signal, it's being taken by this guy and being saved in the microcontroller. It's still in the chip.
Yeah. And
How do you see it?
through the laptop because
A laptop. Yeah, let's use laptop.
you're connected to the chip already.
How do you make connections?
connect
You need
through
you need a
UART.
scissor, right? You need to cut the USB and connect the USB to. No, I'm kidding.
Splice some wires.
What do you need to do? RX over here. I just want to use this RX so my party can see it. What you want to do?
Right?
You already have this one connect to the RX through hardware. USB, you plug in, it's connected. So why not just use the TX1 module to send it? What's the function to send it? Print. You have used it for millions of times, you didn't realize. It's actually a TX sending function. Print. Print F. When you print it in the monitor, right?
Yeah.
Which one is printing? Who is printing? Who is printing? Where is the printing function? Where is that printing function is at? Where is it? In the chip, right? In the instruction memory, in the chip. So who is printing though? The chip. Printing where? Printing to where? To PuTTY. Okay? So it's happening internally inside the PIC microcontroller. It prints, it sends out through TX to where? To RX. It's already hot-wired. So see that on PuTTY. That's how that works. So I was thinking, how do I make the connection here? How do I do it? See here, how do I print it? Data received. Okay? Whatever being received, it's there's a register. You can do EUS art, whatever, read, right? There's a function you can use being created by MCC. You read it to where? To a register, to a variable. URT what? URT what? To read. 2 to read. Why? Because it's connected to UR2 module. Okay? Read it. It's inside. It's a register. It's already inside the chip. It's a register. You can use whatever, you can do whatever you want with it. How do you print it to here? I'm just writing a pseudocode, okay? Just print this, right? Just print it. Done. So this will be, go here and display it. That's how that works, how the data transmission works over here. If you are just sending one character, which is the inLab, what the inLab does, you don't need to create a buffer. I'm gonna show you what the buffer looks like. It's just sending, you send it, press S, it's sent. You couldn't visualize it because it's IR, it's being sent. And the decoder is already on. It's gonna receive it and will, because you have UR2 enabled, so whenever you have a signal appear here with a protocol, right? So what's the starting bit of UR? Pull it down to 0. Whenever this one got put down to 0, it knows that signal comes in. Start receiving the data and being put in a register. It's a receiving register. I think the name of the register is R receiving register B2, I think, whatever, the register, okay? And there's another structure in the circuit that they didn't show the details, so we have to guess. I hate this, but it's okay. So it's helping you to answer some of the questions in the inLab. You just need to know what's happening. You don't have to know the details because I don't even know what the details are. It's okay. They didn't provide you with the internal circuits. They don't want to overwhelm you guys. Also, it could be IP, right? Could be IP here. It's called FIFO. So this is a RX pin. Data comes in. It's being shifted. It's a serial, right? It's one wire, and being shifted into one register. It's called RSR register. RSR register. It temporarily saved it in there. Whenever it reaches, it received 8 bits, it will be latched into a register called FIFO. It's complicated thing, but this is the last question in the inLab. So I provided the answers here on my website, all these descriptions. But for short, let's keep it simple. So I don't know what's really going on in the hardware. I don't know the circuits. Didn't see the circuits. It's not visible to us. So anyway, so whatever the datasheet tells us is FIFO is a first in, first out, right? It's a shift register, first in, first out. So what's happening for FIFO is it's like this: first in, first out. Make sense? Oh, just it's a Q, or it's a Q. So it's first in, first out. And what's happening is the data, when the data is being received, and it's going to directly get into FIFO after being temporarily stored in RSR, the RSR register, which is a shift register. It's going to directly put in here, and whenever the FIFO receives the data, it will put the flag on, the receiving flag. No, it's actually page 4. So when FIFO, first in, first out, receives the byte RC, that's the name of the flag. Name of the flag is RC2IF. Why is RC2IF? Who is receiving? You are what? So why is RC2? It's because you are 2. So it's confusing because UR2, this bit is a flag. It's within the PI R is just register, and PR is 3 register. Anyway, it's okay. It's just register, and that's a field. That's a register. That's a field. It's just 1 bit. So this will be on. So it becomes 1. And when you read from the receiving register, which is called RCR EG2, when you read from this, FIFO is cleared. It didn't show what's the connection between this and the FIFO. I couldn't see it. I don't know what the connections are. But the thing is, data being shifted in, it will be stored in here temporarily. And if you read from the receiving register, which is the data being saved, being stored in, and FIFO will be cleared. It's ready to receive another byte. This helps you answer the questions in the inLab. We don't know. We don't need to know the details of the connections in the digital circuits. So we just need to know that whenever EUS art 2 that dot, right? Dot read underscore read. This function is being called. It's going to return whatever in here. Or the received data. Okay, now let's come back to the code. Any questions on this by far? Not this one. inLab06. I think I open it up here. Okay, so first look at timer 2. 26 microseconds, make sense? Why? 38 kHz. Right? Be repeated for like at least 5 times today. Why 1 to 4 per scalar? Because the table, right? The table, we pick up the correct one. The one works for this period. Okay? Here, nothing fancy. You are 1. Okay. Let me zoom in. So the inLab code is really simple. First step, let me show you the video here first, so you'll know what's going on for the demo. I don't know how the past students how did they do the work if they don't know cannot watch the demo, right? It's just so hard, I think. If you watch the demo, you know what the goals are, right?
Right. For the inLab, first you have to connect the jumper from RC0 to RB7, like what I.
Why RC0 to RB7? RB7, the UR2 is RX. RC0 is what? GPIO, doesn't do anything.
Just did over here. And the second.
Why did I connect the jumper here? That's the RC1. RC1 is jumper. So you can deliver the PWM to what? To BJT.
After you programmed the microcontroller, don't forget to unplug this programmer board, the snap board.
Yeah, you have to unplug it in order to get it to work. I don't know why. We'll figure that out later.
From it. Okay.
Oh, you have to unplug it when you are trying to do the demo. You want to try to run it. So inLab is provided. You download it, put a jumper, make a connection, and unplug. Then start the demo.
Disconnected. And then connect your PI, restart it, Shift Z, and then do a Shift S and Shift R.
So Shift S will send the hard-coded letter. Since in the inLab I put a 0 in there, so it's just a 1 byte. So by sending 1 byte is easy. You don't need a buffer to store all the other characters. It's trying to be sent. It's just a 1. So that 1 byte will be stored in where? Will be stored in where after it's been sent? The FIFO or where? This one. So you are not losing anything. Just 1 byte. Do you need to rush? Like press S, you have to move it fast enough to press R to receive it. Your finger can be as fast as like 1200 bits per second, right? So you're fine because it's being saved in that register.
You can see that just sent 5, the ASCII code is 35, and then the IR decoder just received 5.
How it's receiving that? Because I pressed Shift R as well. So after I pressed Shift S, it's sending. So it's doing whatever I already drew on the paper, like all these protocols, and it's being received by the UART tool. And then I press Shift R. It's receiving, right? And then I have to print it. So in the press Shift R in the case Shift and case statement, when you do Shift R, you are also printing it to UART1 as well. So that's how you are receiving. You are verifying, hey, this is 5 sent by the IR transmitter, and I'm receiving a 5 as well. It's saved in the register. Okay.
So you have someone else point their board at you?
No.
Oh.
Let me show you.
They're just
Where's the IR emitter? Here. Where's the IR receiver? Here.
But can someone else? Could someone send you a message across the room from their IR
Yes.
LED?
Yes.
it's bouncing everybody.
So yeah. So if you press the use the remote whatever in the room, you press it, it should already received and saved in the register, and you can print it to UART. Try it. So I'm curious about that as well. So that's for 1 byte. If you have to do multiple bytes, that's a lab. That's a lab. Multiple bytes. So what's happening is, so here's a diagram for the lab. Okay. So what's happening is you in your PuTTY here in the laptop. Okay. You type a string of characters, and then you send it. So you have to program your PIC to receive byte by byte and save it in array, so you are not losing anything.
How do you decide how big to make your array?
Just don't make it too big. I think 32 is the maximum.
Okay.
Just depending on the system.
Yeah. Yeah. Don't want to make a super long paper, right? But it won't be able to handle that. So there's a limit on the memory. So it's already saved in there. You don't have to worry about losing any of the data. And then when we are doing the transmission, you use the index to take out 1 by 1. You take 1 character, and it's a byte, and use the mask to extract every single bit, so you'll know what kind of PWM you want to send through RC1. Okay? Then this one is sending byte by byte, and this is receiving it, and you are using a certain baud rate, which is 1200. Why 1200? Since you already hard-coded here. Can you make a longer or shorter one? Maybe. We can try it later. But this experiment we are using 1200, and in Lab07 we are using 2400. It's not very sensitive to it. And then received by this one, you take byte by byte and save it into a receiver buffer. Use the index, save it in there, and then send it out, print it out byte by byte. Use the index. Okay. So focus on the inLab. So I think we are good on the inLab because it's easier. And for the lab, I think we can talk more about it on Friday. I'll provide a template here. Okay, we'll talk more about it on Friday. Okay.
Thank you, Professor.